Hi, it's Danny Elegante from A Plus College Ready, here to walk you through the content for Unit 1. As you can see, this content is just review. These things should have been learned in pre-AP chemistry or in just regular chemistry. As a teacher, you'll need to get an idea of what your students know and what you don't know. We've allotted 3.5 weeks in a normal 45 to 50 minute period day to cover this content. We'll cover the things you see listed, and I'm going to just walk you through the basics of what it is. Feel free to fast forward if you think, I already know this stuff. The mole concept is absolutely central to AP chemistry. The students need to be able to convert from particles, atoms, and ions, to moles, from moles to grams, and then from grams to liters. Not only do we go from grams to liters, but we also continue that on, and we can talk about molarity of a solution. Being able to connect all those concepts is vitally important. Once they understand the mole, students can do percent composition, empirical formula, and molecular formula. For example, an empirical formula is simply a matter of finding the ratio of elements in a compound. And they just convert percent to grams, grams to moles, divide through by the smallest number of moles, and that gives you the overall ratio. Once you have an empirical formula, you can create a molecular formula. And the molecular formula really just becomes an issue of what I call a Gazzetta problem. You take the molar mass of the empirical formula, in this example 30.06, and you divide that, or you see how many times it Gazzetta the molecular mass of 60.12, and from that they can derive a molecular formula. Stoichiometry, one of the hardest concepts in chemistry when you start it, but one of the easiest once the students have mastered it, is also very important throughout all of AP chemistry. They have to be able to go from something that's given to something that you're looking for, whether it be grams to grams, or grams to liters, or grams to molarity. All of those things hinge on the kids being able to write a balanced equation. Once they've mastered the idea of stoichiometry, we can go on to things like limiting reactants and percent yield. Limiting reactants is just based on the idea that you're going to run out of one of the reactants before you run out of the other. The way I teach my kids is they start out with grams of each reactant and work it to a common product. Whichever one gives them the least amount of product is the limiting reactant. You may have learned a different way, or you may use the concept of a rice table to break it down exactly how many moles of each thing are produced and how many moles of each thing are used up. In percent yield, it's largely just a task of doing the stoichiometry to figure out the theoretical yield. The problem gives you the actual yield, and the student is able to calculate what percent was actually made compared to what they thought was going to be made. When we talk about solutions, we know that there are ionic compounds like salt or calcium chloride, and when those are introduced into water, they dissociate into ions. They're already ions. Whereas molecular compounds like HCl ionize into ions. Even water will ionize into ions a little bit. Some do and some don't. That's why we have soluble things and insoluble things. It's largely a function of, can the solvent molecules pull them apart? Of course, you'll need to be able to calculate molarity. You will also need to be able to calculate dilutions. And the solubility rules that you may have used for pre-AP or regular chem really come down to one basic solubility rule. That one listed at the bottom. The importance is that AP Chem will tell you a precipitate is made, and the students need to be able to analyze the reaction and see which one is the precipitate. There is no need to memorize a big long list of solubility rules. When we talk about solutions, we also talk about Beer's law. This is something that I hope is covered in your regular chemistry class, but it may not be. Alabama Science in Motion has a lab called Concentration of Solutions, where they let the students use a colorimeter or spectrometer to measure the absorbance of light that you shine through a solution. The more concentrated the solution, the darker it is. So the more concentrated the solution, the higher the absorbance goes up. This equation in and of itself is unimportant. The students just need to know that the absorbance is proportional to the concentration. When you look at a graph that they get from a lab, you can see that the absorbance increases directly proportional to the concentration. Knowing that, AP throws a lot of questions at students and asks them analyze errors using Beer's law, where they might give you a dot on the graph, say here, and say what could cause that. Well, maybe it's that there was a smudge on the glass, or maybe it was set to the wrong wavelength or whatever. Speaking of wavelengths, when you do spectroscopy with Beer's law, it's very important that you pick the wavelength of maximum absorbance. This is the wavelength where the light really is going to be sensitive to changes in concentration. For example, in this graph, you can see that the wavelengths from about 500 to about 575 are going to be the highest absorbance. So if you were going to be measuring concentrations of this dye, you would want to pick some wavelength in that range. Picking a wavelength down here, 600, isn't going to be helpful because it's not absorbing that wavelength of light. Gas laws are also going to be fundamental to AP chemistry, but instead of just memorizing mathematical constructs, the students really need to be able to explain the why. The idea that pressure is gas particles running into things, and that if you have more particles or faster particles, there's more pressure. In the old AP chemistry exam, they had to calculate things called root mean square velocity. That's no longer needed. What's important to know is that temperature is the same thing as average kinetic energy. If you double the temperature in Kelvin, you've doubled the average kinetic energy. For things to have the same kinetic energy because they're the same temperature, atoms or molecules that have different masses are going to have to go different speeds. So I can throw a bowling ball at a set of pins and knock them down, or I can throw a ping pong ball at a set of pins and knock them down. The ping pong ball is going to have to be going a lot faster. We see that in something called a Maxwell-Boltzmann distribution. The idea that the average kinetic energy would be the peak of the hill. So right here in this 100K peak, this would be the average kinetic energy or the average speed of the molecule. As the gas heats up, the molecules spread out in their distribution. There are some going very, very fast, and there are some going very, very slow. And so as the gases warm up, the hill gets lower and more spread out. As the gases cool down, the hill goes up and gets squeezed to the left. But what happens if you have the same temperature but different gases? The largest gas, xenon, is going to be going the slowest. The smallest gas, helium, is going to be going the fastest. In terms of what gas laws they need to know, the first one is PV equals nRT, the ideal gas law. The R values are given to them on the AP equation sheet. No need to memorize those. And again, you need to stress to your students that units are important. Let the units guide them in terms of what R value they will use or what the pressure or volume should be. You can take PV equals nRT and manipulate it around and create the combined gas law. There's no need for the students to know Charles' law, Boyle's law, Gay-Lussac's law. Instead, they just need to know the relationship between pressure, volume, and temperature, assuming that the number of moles of gas is the same. You can also alter the ideal gas law to find molar mass of a gas and density of a gas. So down here, you'll see that the molar mass of a gas can be shown as this way or as this way, density times RT over P. I tell my kids to call that dirty P. And oftentimes on the AP exam, they will give them information and then ask the students to find the molar mass of the unknown gas. One more gas law they need to know is Dalton's law of partial pressures. Basically, you have a bunch of gases in a container. If you add up each individual pressure, you get the total pressure. And finally, Avogadro's law. Avogadro's law is not commonly seen in a pre-AP or chemistry classroom. Avogadro's law is the simplest of the gas laws. If you want more volume in a balloon, you add more gas. You can also extend Avogadro's law to say if you keep the volume constant, if you add more gas, the pressure gets greater. And this is important when you start talking about there's 4 molecules of one gas and it generates 1 atmosphere of pressure. If you have 8 molecules of a different gas at the same temperature and volume, then it will create twice the pressure. When we do reactions in chemistry or pre-AP chemistry, we teach them 5 different types of reactions. There's synthesis and decomposition, there's single replacement, double replacement, and combustion. When in reality, there's a whole host of other reactions going on. So in AP, we think of reactions as belonging in 3 camps: precipitation, acid-base, and redox reactions. The precipitation reaction is just a type of double replacement, as are the acid-base reactions, and then the oxidation-reduction reactions, or redox, are the reactions where something loses electrons and something else gains electrons. When we write equations, and hopefully this is something that they have done a good bit in chemistry or pre-AP chemistry, they need to be able to write a balanced equation and predict states of matter. Then they can take anything that's aqueous and split it into its ions. Anything that's a solid will stay together, and then once they cross out the spectator ions, the things that are the same on the left and the right, you can generate a net ionic equation. If your students have done this in chemistry or pre-AP chemistry, then you are good to go. And when you follow these rules, you generate something like this. You take the totally balanced equation, split up anything that's a strong acid, a strong base, or aqueous, and you cross out the spectators. And that gives you the idea of what's really going on in the reaction. It's important to note that when we talk about things becoming ions, we have to differentiate between strong things and weak things. Strong electrolytes, like salt, are things that produce lots and lots of ions. HNO3 nitric acid is also something that produces lots and lots of ions. Whereas weak things like vinegar or tap water, they produce very few ions in solution. Acids that are strong acids produce lots and lots of hydrogen ions in solutions. Weak acids, on the other hand, only give you a little bit. Acids and bases, in terms of weak and strong, will come up later, but it's enough to say right now that strong acids are HCl, HBr, and HI. I call it Hickel-Hibber-High. And then nitric acid, HNO3, and sulfuric acid, H2SO4. The weak acids, they do give off some ions, but not very much. And these are things like vinegar, acetic acid, formic acid. And pretty much anything that's not strong you would classify as weak. More on that much later on in the AP curriculum. Bases also give off ions, and anything that's a group 1 hydroxide, sodium, rubidium, cesium, lithium, is a strong base. Weak bases, usually they will tell you it's a weak base, but ammonia is a classic example of something that doesn't give off a whole lot of ions. The precipitation and acid-base reactions are therefore pretty easy. The redox reactions are going to be a little bit trickier. Now in Unit 1, we are going to do a very, very simple idea of redox. And in Unit 2, they're going to hit it much harder. They're going to talk about electrochemistry and do some balancing of complex redox reactions. For right now, it's enough that the kids know that an element all by itself, like oxygen gas, has the oxidation state of 0. If you have an ionic compound, MgO, then the oxygen would have an oxidation state of -2, because that's its charge. The magnesium would have a +2, because that's its charge. Most of the time in a compound, oxygen is going to be -2, and most of the time the hydrogen's a +1. If your kids get that right now, then they're good to go. In Unit 1, we're only going to give them single replacement reactions, or maybe a combustion reaction, and ask them to say, is this a redox reaction or not? And finally, the idea of what is oxidation and reduction. Oxidation is when something loses electrons, and reduction is when something gains electrons. So in any battery, there's one thing being oxidized, giving up electrons. Those electrons flow through wires and come back, and they reduce the other end of the battery. So as long as your kids know that simply electrons lost or gained, and that is the definition of those two, they are good for Unit 1. One more last note in general about Unit 1. You're the teacher. You're a professional, and we trust that you know what's best for your kids. So you might have to backfill a little bit more or a little bit less, but we've tried to give you enough resources where you can do what your kids need. So the key to AP Chemistry is not standing up there and lecturing to them all the time. The key is to let them explore it a little bit, see what they remember, backfill and fill in problems with students as they come up, and you'll find that the student will be the hardest working person in the room. And after all, that's the goal. Thanks a lot and good luck in Unit 1.